Hey there, welcome back to Short Text 331. Today we continue our discussion of machine learning, and we're going to talk about something called the stochastic gradient descent algorithm. And if you recall, the last time, that was our first video on machine learning, we talked about neural networks, and you can think of a neural network as a complicated mathematical expression that connects some input vector with an output A, that we call A here, which is the activation of the output layer. And at each instance here in this cartoon, you have layers of neurons, and each neuron will have its weights and biases, and together all this neural network then will have a bunch of parameters, which are the weights of all of the neurons and the biases of all of the neurons. And our job then is to optimize the weights and biases such that this output A matches some desired result Y for a given input X. And so we have then some data that's given to us where an input is associated with an output, and then we want our neural network to match that output Y. And let's say that we have n samples, data samples, and usually in practice you want to divide these n samples into a training set and a test set. So this we're going to use to adjust our parameters, W's and B's, and then the test is going to be to decide how good that fit is. And to optimize this network, we need to choose a cost function, which is going to encode, if you want, the cost of making a mistake. So whenever we get the wrong answer here, that is not the desired result Y for a given input, then we have to associate a cost of that. And we want to minimize that cost. We're going to call that cost function C, that depends on W and B, so all the weights and all the biases. And I'm going to leave it at this, at W and B, but of course this W will have indices associated with the layer and with the neuron, and this B's of course will have indices associated with the layer and the neuron as well. And so to attack this problem of minimizing this cost function, what we have is a multivariable calculus problem. And so to tackle that problem, we will use the so-called gradient descent algorithm, or that's what one would normally use. One would try to use gradient descent, but we'll see that that is very costly. But first, let's talk about gradient descent. So the idea of gradient descent is that to minimize this function, we would calculate the gradient vector that we call here gradient of C, which is of course just a vector of derivatives, the partial derivatives. This is dc dw, the derivative with respect to w, and dc db, the derivative with respect to b. And what we want to do is we want to move in the space of w and b, but in the opposite direction as the direction marked by this gradient of C. And why is that? Because if you recall, the interpretation of the gradient is that the gradient points you in the direction of fastest growth. And so we want to go in the opposite direction, the direction of fastest descent. And so if you start our search for our minimum of C of WB at this point, W0, B0, then we want to update our point to a W1, B1 point, where we take the previous point and we subtract a small quantity, or typically a small quantity, times the gradient of C. So this minus sign together with the gradient of C will then point us in the opposite direction of the gradient. So that's why we go downwards in the direction in which C of WB decreases. And then this parameter we can adjust to make sure that we don't take steps that are too large. And so this is a free parameter that sometimes is called the learning rate. And so we want to adjust this so that we don't take steps that are too large, but also not too small. If you take steps that are too small, then these iterations will not converge very quickly. And if you take them too large, then you may jump around your space too fast, and you may not get to the minimum. And so regardless, if C of WB does have a minimum, then this algorithm, again, by tuning eta appropriately, will take us, at least intuitively, it seems geometrically, will take us to that minimum. And it will for sure take us to a local minimum. It may or may not be the global minimum, but that's the idea then of gradient descent. Now, why is that not something that we would do with our neural networks? The problem in practice is that we would have a lot of parameters and a lot of samples that we need to fix those parameters. And so usually this C of WB will be a sum, which here we've divided by nt, the number of training samples, and we have to sum over all of them functions that encode the weight for each of the samples, or rather the cost of each of the samples. So again, remember that we have for each of the samples we'll have a desired output, but we also have a given output that the network gives us, and it will not typically match what we want. And so our job then is to adjust the parameters. And so And then what happens is that we sum over the cost of each of those samples, and here's a typical cost that you might see, which is called the quadratic cost. So here we have C sub I of WB, the cost of deviating for sample I from the desired result is given then by difference squared. So we have W sub I minus A, which is the network output evaluated at that point X sub I with the weights and biases that are given at that point, and then the whole thing squared. If we sum over all the samples, then we'll have the cost associated with those weights and biases. So then the cost associated for the network that we have at that moment. There are other choices for the cost functions, such as this one, the cross entropy, which there are reasons to choose this one rather than the quadratic cost. We'll come back to the discussion of quadratic cost, cross entropy, and such in a future video. But this is basically the structure. The structure is such that you have a lot of variables, W and B, and you have a lot of terms in this sum, because ideally you will have perhaps millions of samples that you want to optimize. And so then calculating that gradient for all the samples is prohibitively costly. And so what people do normally in this situation is that one takes mini batches to perform an approximation. So this is the idea of mini batches. Suppose then that you have your number of training samples and you subdivide that into big M mini batches of randomly chosen samples. And so then you have a little m size of your mini batch. So imagine then you have all your samples and you take them. Suppose you have 50,000 samples or 100,000 samples and you take them 1,000 at a time or 2,000 at a time. That's your size of your mini batch. And so you'll be left with however many mini batches of such randomly chosen samples. Because they're randomly chosen, this is the stochastic part. And so this is where the stochastic part of stochastic gradient descent comes in. And the idea is actually pretty simple. So we want to estimate our gradient. And we I just said that this sum over all the samples and doing this gradient for each of the samples for the whole set is very costly. And so what we're going to do is we're going to proceed by doing a minimization for a bunch or a batch really of samples at a time. And so we'll calculate this average over a given mini batch, and then we'll use that in gradient descent for some number of gradient descent iterations. So we're going to optimize with respect to that mini batch. And what we do next is we go to the next mini batch and proceed to do the same thing. We do gradient descent iterations over this form, the new form of the gradient now with a new mini batch. And so the function is always the same, but we're estimating the gradient by using different mini batches of our whole sample set, which would be the exact result, which we don't have access to because it's very costly. So this, in a way, then introduces an error, but also it allows us to calculate, because then it would be much better instead of doing 50,000 terms here to do 1,000 terms. So that would be 50 times faster. Or if you choose a mini batch of size 2,000, then you'll be able to go 25 times faster than if you use the whole 50,000 samples all together. And so this is important because you will be doing a number of gradient descent iterations over this function. So you're going to be calculating this many times. And so once you're done with your mini batch and you're done optimizing for that mini batch, you go into the next one, and so on until you've exhausted all your mini batches that make up your total number of samples. And at that point, we say you have completed an epoch. So after m mini batch rounds, so you've optimized this, then m times, and you've gone over all your mini batches, then you have completed an epoch. And so what we do then is we go on to back to the beginning, and we choose a different set of mini batches, and we resample everything, and complete then a new set of m mini batch rounds of optimization. And as we go, then the idea is that we'll be reducing the cost of this function, and as we go epoch after epoch after epoch. So this is the type of graph that you might see in some books of how the cost function hopefully behaves as we go epoch after epoch and so on, optimizing the function as we go. So for neural networks, it turns out that this gradient of C sub I can be calculated very quickly using an algorithm called backpropagation. But we'll talk about that next time. But this is the idea then of stochastic gradient descent, that you perform that by approximating the exact gradient with a stochastic approximation of it by taking samples or by taking snapshots or chunks of your samples that we call mini batches. That's about it. That's all I have for you today. I hope you found this instructive and useful. And if you did, and if you like these videos, please consider liking and subscribing to the channel. And as always, if you are looking for a tutor in physics or math in English or in Spanish, you can contact me at shorttext331@gmail.com. And or you can leave a comment in the comment section below and I'll get back to you. I'll see you next time.